So we just finished the lecture. I'll watch these in order, by the way. I just recorded and finished recording the daylight factor study, and this is the second lecture to cover the direct gain solar study. And before I get started on this, I'm going to show you where the reference material is from the book to get to that information. Is in this module. If you wanted to see it, I'm plucking out just the direct gain portion of the chapter on heating and cooling. And we're going to be following along with the steps that are involved in the sample problem, but I've just made up my own problem, but I'm going to be interpreting this for you so you can see exactly what do these steps entail. The first part of it, so let's start at the beginning of this chapter. Direct gain is one of the simplest ways of gaining solar heat for your, or using solar heat for your home. What you need are two things basically. You need basically a wall of windows, and then you need something that will store that solar heat over the course of the day, and then is able to release it as radiant heat at night when the sun goes down. So the chapter covers some of the things to be considered of, and certainly this relates directly to the direction your south side walls are facing. Those are the walls that need to have the solar apertures. And then this table here under thermal properties of various materials shows you the number of BTUs that can be held and the capacity of these different materials based off of their based off of per pound or density and their heat capacity. So what I'm using in this example is concrete, 6 inches of concrete. And so that 6 inches of concrete, I don't know what it weighs, what 1 pound of 6-inch concrete would be, but this gives you some idea of its thermal properties and what it can hold for capacity as far as BTUs and release later. Let's see here. So design procedures. Let's go ahead and go on to this. So the first step is to estimate the required size of the solar apertures, which is basically your glazing. What size do your windows need to be? And we're going to be using these ranges that are given to us in the book, which we have a range of 0.2 to 0.4 square feet of window area, basically, south-facing window area, based off of for every 1 square foot of floor area, heated floor area that is in the right place to be able to accept direct solar gain. And we are in colder temperature climates, so this is the correct range for us to use. If we were in milder temperature climates, you have these ranges here to use. And then if we get into warm climates, we would be using cooling loads rather than heating loads. So the next step is to estimate the amount of thermal storage required to support the proposed glazing. So this is one piece of it. I got to figure out how much glazing I need, and then once I figure out how much glazing I then need to figure out what's the floor area that I need in order to store all that heat that I'm going to get from that glazing. So these are directly related. So we're going to see what happens when we look at my example house. And so I've got a concrete mass of 6 inches, and it can hold about 3 times the area of the solar glazing. So that's the ratio. It's a 3-to-1 ratio. And that's going to be important for us to use that information properly to calculate the rest of this. And then this talks about reflected radiation, which is a little misleading because I'm not bothering with that because we're not my example house, I'm not doing reflective radiation. It's just the sun's going to hit that concrete floor and it's going to start retaining that heat. Step 3 is to estimate the non-south building envelope. So that means 3 of your walls are going to be calculated. You're not going to calculate your south wall at all. And then you're going to exclude the windows and doors that are only on those non-south facing walls and remove those from your calculation. So you're essentially doing a surface heat loss calculation for a single day on the 3 sides of your building, north, east, and west. And you're also going to calculate the loss through the windows and apertures on those sides. And you're also going to calculate the thermal loss through the roof, okay? And you're going to figure that out based off of how many BTUs you're losing in a single day. And then you're going to divide that by the heating degree days that we have in this area. And that's going to give you your net load coefficient. Okay, so I'm doing an overview of what we're going over, and then you're going to see it in action with the example. Now, where we live, we are just a little bit over, we might be closer to this value now because of global warming, but we're at, if you look in the local weather stations and things for this area, some of you did this already. We found that we could get a more accurate reading for heating degree days, but it's somewhere around 7,000 to 7,200. And I think I ended up using 7,200 in my calculations because I think that's the heating degree days that they give this area in the IRC or something like that. So I just use that. And then the last bit here is if the estimated net load coefficient is greater than the target net load coefficient, then the improvements in the building performance are necessary to reduce the heat loss. If the net load coefficient ends up meeting or being the same or less, then you have the potential to have a completely solar heated house. Okay, so that's the deal. That's how this works. So this example project over here is what I used as my guideline, but I'm going to break it down in those same steps. I did that over here. So here's the same building, and we'll start off first of all by determining the required size of apertures or windows. In Maine, we are in that range of 0.2 square feet to 0.4 square feet per 1 square foot of floor area. So in this project, what I've decided to do is use all of this space right here from the entry into the living and dining and kitchen, because all of that space has the potential to be able to get direct solar gain. So that's adds up to 705 square feet. So that's an important number. So when you look at your floor plans, don't just take the entire floor. You're going to take the portion of the floor that actually has the ability to have direct gain from solar radiation heat, okay? So if I take that number and I put in 0.2 square feet of window area times 705 square feet of floor area, at the low end, I would need 141 square feet of window area in order to make this design work. If I use the higher end, I do 0.4 times the 705 square feet, and I end up with about 282 square feet of window area required. Okay, so that's one piece. So I know that I've got a range here, and I want to see which ones, would either of these work, or would one work but not the other, okay? So I know that it seems like we just worked it all out. We've got the 705 square feet, we've got our windows, but there's a different ratio that we're using for, remember, the storage, the mass storage of thermal storage that this floor is capable of holding. may not be the same as this ratio that we have up here for the windows and square footage. In fact, it's not the same. So we now have, let's take the low end here. This is saying for each unit area, meaning for each unit area of window, we need 3 unit areas of primary thermal mass. And that means I need to have basically 3 times the square footage of this window as floor area for this to work. So if I take the 141 square feet of window unit area times 3, I need 423 square feet of floor area. And that would work because I've got 705 square feet of floor area. So I have more thermal mass than needed if we go with the lower range, okay? And that lower range is based off of that 0.2 square feet of floor area per square foot of floor area. If we use the higher ranges, which is probably more likely in Maine, then we are looking at needing 846 square feet of floor area, which exceeds our available primary thermal mass by 141 square feet. This was just a coincidence that that ended up happening, I think. So what does that mean? This is considered our primary mass, and a secondary mass can be a vertical partition wall like I've got here. But the secondary mass can't be counted as being equal to the primary mass. So I have to treat it with the correct ratio. Basically, a secondary mass that I put in as a vertical wall to absorb the heat can only absorb the heat in a 2-to-1 ratio, or 1-to-2 ratio, I should say, compared to the primary mass. So that means I basically need to take my 141 square feet and double it. And if I double it and I'm able to create a vertical wall mass of that value, 282 square feet or more, then I could make this work. It just so happens that my CMU block walls here add up to be approximately, because they're 10 feet tall, remember, end up being 297.4 square feet. So this is possible. This is doable. It is possible for us to heat this house using direct gain passive solar, but we really need to do a little bit more work to find out if we actually hit that net load coefficient. Okay. I know this is a lot of math. You're going to get hit with this a few times, but at least it's in a video. You can rewatch it and see if it can make it make sense to you. It took me about 3 or 4 times reading the chapter on solar gain, direct gain, before I finally figured out what the heck they were talking about. But I finally did figure it out, and it does make sense. So the last step, the third and final step, is where we have to do math very similar to what we did for heat loss calculations. In fact, it's pretty much the same. And I don't think we need volume in here anymore, because volume doesn't come into play in this. This is all surface heat loss, not volume. So estimate the non-south facing building envelope. So if I take my wall surface area on these 3 sides, and I did this measurement from the inside of the wall rather than the outside, because that's the surface area that's being exposed to the outside. I ended up with 972 square feet of walls. And then we've got 1,400 square feet of roof above us that are exposed to the outside. The walls have 1, 2, 3, 4, 5, 6, 7, 8 windows. Actually, I started off with just, because I added these windows in the last lesson. So I actually had only 7 windows, I think, to begin with. I estimated all of them at the same size, about 12 square feet. So and then I added this door in. So those added up to 119 square feet of window or door openings in the wall, and I subtracted that to make the wall square footage is 853 square feet. My wall performance for this project is R49 or a U factor of 0.02. My roof performance is a little bit better at 60 or a U factor of 0.016. And then my window and door performance is about the same. It's high end because I've got, triple glazing and low E and all that. So I've got a 0.03, which is pretty good for a window and door. So when we do our math, this is our area times the delta T, which is our change in temperature. I use 65 degrees compared for the inside compared to 32 degrees on the outside. So I had 33-degree change in temperature. 0.02 U factor times 24 gives me the 13,512 BTUs lost per day of wall surface. I did the same thing for roof surface. It's the same formula. And then the same thing for windows and doors. That's the same formula. Add all those up and we get the total BTUs, a total surface BTUs lost. And then we're going to divide this number by 7,200 heating degree days. And we get a net load coefficient of 4.73. Our target is between 4.6 and 3.6. This doesn't quite meet that target. So what that means is we've got to make some minor improvements to the building envelope, and things like as small as, remember I added this window in the daylight factors. Well, that actually works against us and makes that net load coefficient go even higher because it changes my window area and door area, which is adding quite a few BTUs as our heat loss. So one of the things that I would do if I wanted to bring that number down and closer to the target is look at removing more windows from those other non-south facing walls and seeing if I could increase my thermal performance that way, or improving on my window and door performance, but these are pretty good to begin with, or building up my thermal performance in the walls maybe, instead of R49 trying to get an R60 with my walls as well, and I probably would make it. So where did this net load coefficient target area come from? That came also from your book. On page 134, it looks like, you have an annual heating degree days and target net load coefficient. And we're in this area right here, so we're looking at 4.6 to 3.6. That's why I put that range in there. And we are just above that at 4.73, which is pretty darn good. So the way that this house has been designed so far has a potential to be successful with solar heating. We look at the 3D view, some of the other things that we could do to maybe make improvements, but it would end up having to have us change our square footage of wall area that we're using is to pitch this roof and increase the window aperture size for the sides and bring in some more sun in on this side, and lower the walls on this side. So if we heighten the walls by 2 feet on this side and lower the walls by 2 feet on that side, we actually end up with the same wall square footage that we calculated to begin with. So doing things like that are some of the ways that you can kind of fiddle with the roof pitch and things to try to get this to work. So in some cases, you're going to find that your daylight factor study, especially on the sides of the building that are your non-south facing, may be fighting you for that direct gain solar study. So you've got two of these things to look at, and you're going to try to find a happy medium. I'd have to say that this design seems like it's going to be, it might actually work with a little bit more tweaking. So that gives you an idea of what you're going to be looking at. So you need to start to scrutinize your spaces like this and see what you might need to do for window sizes or roof pitches to maximize your potential for both of these areas.